On to Bobby. So Bobby Kleinberg is a professor of computer science at Cornell University. Let me read his citation. It's for advancing our understanding of online learning and decision problems and their application to mechanism design. So congratulations, Bobby, and over to you.
Thank you. I'd like to start by saying how honored I am to receive this award, and really sincerely appreciative of the committee and the community for giving me this recognition. It's especially exciting to share the award with Michal, who I also thank for concluding her talk on the theme of it's okay to be approximately optimal rather than optimal, a theme that I'm planning to demonstrate with this presentation. Oh, yes, that's right. We'll probably put a sentence to that effect in the call for papers. So in 2003, I wrote my first paper on economics and computation. It was also the first time in my adult life that I engaged in a creative act whose outcome I was truly proud of. And this talk is, the paper that I wrote that year contained the seeds of most of the work for which I believe I'm being honored today. And this talk is the story of how those seeds sprouted and of my gratitude to the people in this community who inspired me and helped me to nurture some of them to maturity. So the story begins in 2002 when my advisor, Tom Layton, invited me to fiddle around with him on a question that had been asked to him by someone at Ticketmaster. They said, you know, we're selling tickets, we never know exactly how much people are willing to pay for seats, and we'd like to know if we can run an algorithm to experiment with prices for tickets and try to learn the optimal price from interacting with the market. And he said, you know, do you think we could come up with any ideas on that question? And my first reaction, fortunately, was not to look at the literature, but to think about this problem in a completely naive way, the most naive version of that question that I could think about. Had I looked at the literature, I would have found out that economists had been thinking about this question since the 1980s, and that in computer science, people had already begun to write papers which turned out to be very influential on our work. But in some sense, it's fortunate that I didn't know about any of this stuff, because I think, you know, had I seen these papers, I probably would have said to myself, well, the problem is basically solved. By coming at it with a fresh pair of eyes and thinking about it in a completely naive way, right off the bat, I managed to find something that, in a toy model, that I thought was pretty interesting. So I said, suppose that all the buyers have exactly the same valuation V, and the only party that doesn't know what this number is Ticketmaster. What should they do in that case? Well, you could always do binary search. You just start out by asking a price, which is the midpoint of the interval of potential values. And you know, if the first person buys at that price, now you know that V is in this subinterval. You keep dividing it in half. And after log t experiments, you have an interval of length 1 over t that's guaranteed to contain the value. At that point, you can stop experimenting and just ask the lower bound on that interval, and it'll only cost you t times 1 over t for the remaining, the opportunity cost of not finding the exact value. So that's a binary search algorithm that has log t regret, and the thing that I found interesting was because there's an asymmetry between offering a price that's too high and too low. So too high, you lose an entire sale. A price that's a bit too low, you just have the opportunity cost of not quite hitting the optimal value. There's a better algorithm based on repeated squaring instead of repeated halving that gets ordered log t regret instead of log t. So in one sense, this is a small improvement. In another sense, it's an exponential improvement. And rather than looking at it quantitatively, I just thought it was qualitatively interesting that for this problem that looks very much like binary search, there's something different you can do that is even better. This turned out to be optimal. And that was the first signal to me that there was something interesting in this problem, and it was worth digging further into it. As further evidence that it was worth digging further, Renato Pajlem and John Schneider, in a paper that I urge you to read if you don't know about it, dug into the multidimensional version of the search problem, where you're searching for a price vector instead of a single price. And they dug out a nugget of pure gold. They extended the log-log-t theorem, but using a very subtle and surprising geometric argument that of all the papers I talk about in this presentation, this is the one that I most regret not having come up with myself. After moving beyond this toy model, we of course wanted to understand what happens when you don't assume that everybody has exactly the same value. And it turns out that that question, we were able to answer it, and it relates to the multi-armed bandit problem. The multi-armed bandit, as many of you probably know, is this famous model of learning and experimentation, which is thought to capture in a very sharp mathematical form the dilemma of exploration versus exploitation. And what you can do in this pricing problem is something very naive that other people had basically done before. You could discretize the price interval into k pieces, choose the value of the parameter k optimally later on. You just treat those k prices as arms of a k-armed bandit. You forget everything else about them. Prices are ordered. Never mind that. I forget that they're ordered. I just think these are k independent alternatives that I can experiment with. And you just run a bandit algorithm as a black box and use that to select your prices. And amazingly, although that algorithm is so naive and is throwing so much information away, we were able to show in two interesting settings that it's optimal up to logarithmic factors. I want to say this algorithm, although it's technically did not appear in prior work because of how we did the discretization, but morally the algorithm is due to these papers of Bar Yosef, Kumar and Wu, Blum, Kumar, Rudra and Wu, Blum and Hartline, that were basically doing the same idea with a different discretization. The thing that I was really excited about in our paper was not the algorithm, but the lower bound. So I want to spend a minute telling you why I thought the lower bound was exciting. I have to give you a picture. This is not a proof by picture, but just kind of a picture of what I found interesting about the lower bound. The trouble is that for the k-armed bandit problem with IID data, there are logarithmic upper bounds on regret. And we were trying to prove a square root of t lower bound, so exponentially stronger. So we had to use some principle other than what works for the finite armed bandit. And it turned out that what was going on in our problem was you can have a continuum of different potential distributions for the buyer's value. And I'm here plotting the revenue curve, so the expected revenue of offering price P for two different potential value distributions. And in our lower bound construction, they all have this shape where they're kind of concave in the middle of the distribution, always peaking at the same height, but you don't know where the location of the peak is. And now the price setter faces a dilemma, which is you can set a price near the optimum, which is cheap in terms of regret, but extremely uninformative in terms of information because the probability of purchase at that price is almost exactly the same under the red model of demand and the blue model. Or you can set a price that's far away from the optimum, which is expensive in terms of regret, but the experiment that you're doing at that price is much more informative of whether the demand model is the red one or the blue one. And so what I thought was neat about this proof is that it actually reveals that there is a conflict between exploration and exploitation. Quantitatively, the fact that you cannot do both at the same time was the revealing part of the proof. And surprisingly, in the regret analyses for k-armed bandits, the lower bound proofs did not actually reveal any trade-off between exploration and exploitation. The theme of those lower bounds was no matter what experiments you do, at the end of t steps, you will not know what the optimal arm is, and so you're going to pay a high regret. So, that was the theorem I was proud of in that paper. And I can't resist telling you in an aside, In a later EC paper with Peter Fraser, David Kempe, and my brother, we again revisited this exploration versus exploitation trade-off in a model with a platform that wants to explore and myopic agents that it is incentivizing to pull arms on its behalf. And there you can actually plot a figure showing the cost that you have to pay people to do the exploring for you and the opportunity cost of when they are myopic and exploit too much, and get a very sharp quantitative result that the shape of the trade-off curve happens to exactly match the shape that you may have made in elementary school when you did this art project with strings and a piece of paper. I know I did. So that was sort of the kickoff for my getting interested in dynamic pricing. What happened next was I took David Parks's economics and computation class at Harvard, which was just a thrilling environment of scholars striving together to learn this new area that was just taking shape. And as a final project in that class, Mohammed Taghi Hajigayi and I thought about the question, how should one do dynamic pricing in the setting where supply is limited? We worked with David on this problem. The very first thought that I had was, well, the extreme case of limited supply is only one good for sale. That sounds a lot like the secretary problem. And so our first paper was, sort of bringing together the secretary problem and online mechanism design to get a 1/E approximation to first best social welfare. I went on to look at the setting where the supply is greater than 1 and had a SOTA paper where I show how the approximation factor converges toward 1. And much later on, with Moshe, Shedin, and Alex, we returned to the setting of posted pricing rather than auctions, where again you're in a multi-armed bandit type environment, and again you get this kind of square root of k dependence on supply. That paper led to thinking about a generalization to multidimensional budget constraints that we called the bandits with knapsacks problem, and with my student Ashwin Badiniduru, we also got square root regret bounds for that problem. But so you see, it was all sort of a very natural and organic outgrowth of thinking about dynamic pricing and what happens when you insert a supply limit into it. Another outgrowth of this thought process was, now that I was tuned into secretary problems and the fact that they had interesting CS applications, I got to thinking about what if you have combinatorial constraints on the sets that you're allowed to select. Actually, a good story to tell on the eve of this year's SOTA deadline. The multiple choice secretary paper that I referenced on the previous slide, the day before submitting it to SOTA, I already had all the results proven, and I thought, well, the paper seems kind of thin. I wonder if I can also prove this result for matroids. I have a day, and most greedy algorithms, that work for picking one element also work for matroids. So 20 years later, the conjecture is still open. But I loved working with these 3 people on it. And thinking about those combinatorial optimal stopping problems naturally led me to learn about profit inequalities, which sort of model the Bayesian version of the same auction theoretic questions that I've been asking. And so there's also a line of work in which I've been thrilled to take part, and also some of these wonderful authors have made great contributions to it. Michal also has made great contributions and sort of gave you, brushed up against profit inequalities near the end of her talk. I need to move into my concluding sequence because I have 1 minute left. So, so the bandit, the secretary, the prophet, these have been my constant companions throughout my research career. And I've explained to you how they all came into my life through the door that was opened by starting to work on this paper that Tom invited me to think about with him. And when I think about what I have taken away from this experience, at the start of grad school, I was not planning to go into economics and computation. In fact, I thought I was going to become an algebraic topologist. And I became discouraged that research in that area seemed to me a lot like a cubist painting. sort of beautiful but starkly abstract and barely interpretable to most people, only interpretable by a few who spend years studying how to decode the symbols. And what this community has shown me is that research can be like a cubist painting, but more like this one, colorful and playful, and using abstraction not for its own sake, but as a reflection of the real world. And so I dedicate this talk to you, my academic village, who have, for the last 20 years, been playfully inviting me to join the party with you. And sorry, this is a slide where I memorized my lines. And now it's escaping me. Right. Thank you all for letting me come along with you on this fun journey. And let's party on.
Well, I hope you can all see how unfair it is of us to have given each of these speakers only 15 minutes, and at the same time, why we felt that both of them needed to be awarded. So thanks to both of you. We unfortunately have time only for one or two questions quickly while we transition to the next speakers in the session. So I'll invite the next person to come set up, and in the meantime, take a question or two. Well, while we're waiting, I'd also like to thank Bobby for not making fun of the dorms.
The rest of us want to thank me half for making fun of me.
So I suppose at this point it's traditional for me to have prepared a question for Bobby, but it didn't even occur to me to do that because I was sure that people were going to have things to say. Do you have things that you wanted to say from the end of your slide? Oh, here we go, one of your co-authors.
In certain circles, it's traditional. It's traditional to ask when you think the P versus NP problem will fall. But let me ask you when you think the Matroid secretary problem will fall.
So when Volker Strassen gave his Knuth Prize talk, he surprised the audience with the provocative conjecture that the exponent of matrix multiplication is strictly greater than 2. So maybe I should use the opening you just presented me with to make a provocative conjecture that the matrix secretary conjecture is false. And I'll steer clear of predicting when someone will find a counterexample.